So welcome everybody to the first talk of the year. On behalf of the IEEE MTT-SCV Santa Clara Valley San Francisco Joint Chapter, I would like to welcome you to the first technical presentation of the year. I apologize on behalf of the chapter. There were some security breaches. We had some people spamming obscene text messages and such. So we've managed to remove them for now. Hopefully the measures we took will keep them out. So moving on to the talk itself, we had a very strong response in terms of registration. We had more than 650 people registered, and already we can see a lot of people are joining the talk. So we hope to see close to 200 people in the talk today. So the title of the talk today is Fundamentals of Millimeter Wave and Sub-Terahertz Frequency Generation Synthesis Radiation for Multi-Antenna Arrays and Transceivers. Our speaker, very distinguished speaker today, Dr. Payam Heydari, who is a distinguished microwave lecturer, IEEE MTT-S. So before we get to the talk itself, there's a few things to note. So to take us through the agenda for today, I would like to invite our secretary, Mr. Venkata Ramagade. Venkata, let me see, I should be able to unmute you.
Hi, Utkarsh.
Yeah.
Hello, everyone. Yeah, sorry again. We had some issues and hopefully we resolved them now. So thank you everyone again for attending the first MTT-SCV chapter's talk this year. I will introduce the agenda for today and go over some of the logistic items for this meeting. Utkarsh later will also introduce our speaker today and go over the abstract for the talk. And we will have a Q&A session as well, as we progress through the talk. Next slide, please. Yeah, a few things to note. So this meeting is recorded on Zoom, and we will send out the meeting slides and the recorded video to all registrants. Please make sure that the cameras are turned off and microphones are muted to help avoid any issues, bandwidth related, background noise, any other issues. Please post your questions in the chat window to everyone. We will take breaks periodically and try to get the answers. Next slide, please. Please also ensure that your display name in Zoom matches the one you used to register. This will make it easier for us to check you in. And as we are actually going through the talk, we will be registering all the participants. And if you did not register and you were forwarded the link to this meeting, please send a private message to me in the Zoom window with your name, email address, and your IEEE member status. Whether you are a member of IEEE or not, whether you are a member of MTT-S chapter or not. We will register and check you in. The next slide. Yeah, and please support us by becoming a member. Here are the links for joining IEEE. And here is the link for joining the MTT-S chapter. And you guys can follow us on LinkedIn as well. There is a hashtag MTT-SCV. So please try to follow us on LinkedIn. The next slide. So for updates on the COVID pandemic, so we will continue having all our meetings and office meetings and technical meetings in the online webinar format only until further notice. So let me also introduce our chapter officers for this year. I would like to introduce our chair, Utkarsh Unnikrishna, Vice Chair Thomas McKay, Secretary myself, Venkata Gade, and Treasurer Tan Toy. Yeah, that's our office roster for this year. And I would like to hand over to Utkarsh for introducing our speaker for today. Thank you.
Thanks, Venkata. So it's our great pleasure to have with us Dr. Payam Heydari. So Dr. Heydari received his BS and MS degrees honors in electrical engineering from Sharif University of Technology in 1992 and 1995, respectively. He received his PhD degree from the University of Southern California in 2001. He is currently a full professor of electrical engineering at the University of California at Irvine. His research covers the design of terahertz, millimeter wave, RF, and analog integrated circuits. He's the co-author of 2 books, 1 book chapter, and more than 140 journal and conference papers. He has given the keynote speech to IEEE Global SIP 2013 Symposium on millimeter wave imaging and communications. He also served as an invited distinguished speaker to the 2014 IEEE Midwest Symposium on Circuits and Systems and gave a tutorial at the 2017 International Solid State Circuits Conference, ISSCC. He has served as a distinguished lecturer of both the IEEE Solid State Circuit Society from 2014 to 2016 and IEEE Microwave Theory and Technique Society, that's MTT-S 2019 to 2022. And it's in that capacity that he's here with us today. Dr. Heydari is also the recipient of the 2016 to 2017 UCI School of Engineering Mid-Career Excellence in Research Award, the 2014 Distinguished Engineer Educator Award, and a host of other awards, including but not limited to the 2005 IEEE Circuits and Systems Society Darlington Award, and the 2005 National Science Foundation Career Award, the 2005 Henry Samueli School of Engineering Teaching Excellence Award, and the Best Paper Award at the 2000 IEEE International Conference on Computer Design. He was recognized as the 2004 Outstanding Faculty in the EECS Department of the University of California at Irvine. His research on novel low-power multi-purpose antenna, multi-antenna RF front ends received the Low Power Design Contest Award at the 2008 IEEE International Symposium on Low Power Electronics and Design. The Office of Technology Alliances at UCI has named Dr. Heydari one of the 10 outstanding innovators at the university. He is currently a member of the International Technical Program Committee of the ISSCC, an associate editor for the IEEE Solid State Circuits letters, and a member of ADCOM for the IEEE Solid State Circuit Society. He has served as the guest editor of IEEE Journal of Solid State Circuits and associate editor of IEEE Transactions on Circuits and Systems. He is an IEEE Fellow for contributions to silicon-based millimeter wave integrated circuits and systems. Going on to the talk itself, the title of which is Fundamentals of Millimeter Wave and Sub-Terahertz Frequency Generation, Synthesis, and Radiation for Multi-Antenna Arrays and Transceivers, or multi-antenna array transceivers rather. So the description of the talk is as follows. Operation in the millimeter wave and terahertz bands has gained great interest due to abundance of unutilized spectrum and resurgence of new applications in wireless cellular communications, most notably 5G. If combined with spectrally efficient demodulation techniques, millimeter wave and terahertz wireless communication has the potential to achieve multi-gigabit per second wireless data rates. In addition, the operation at higher frequency gives rise to smaller size passive components, most notably antenna, making it possible to design and implement massive phase array or MIMO systems on a single die or single wafer. As the communication system schemes, including spectrally efficient demodulation and carrier aggregation techniques, are making progress at RF frequencies, far more challenging requirements will be imposed on the oscillator and frequency synthesis design. Increasing the carrier frequency towards the millimeter wave terahertz regime only makes these requirements more stringent. This lecture, which is one part of actually a series of lectures, will focus on the fundamentals of millimeter wave and sub-terahertz frequency generation, synthesis, and radiation for multi-antenna array transceivers. So with that, Dr. Heydari, I would like to hand it off to you.
Thank you very much. So can anyone see my screen?
Yes.
Okay. So thank you very much for the introduction. This this evening, I'm going to go through the fundamentals of millimeter wave frequency generation, synthesis, and radiation. And if you notice, this title is a little bit kind of slightly different from what was introduced, because I just thought that covering the whole notion and concept of frequency generation, synthesis, and radiation requires more than 1 hour of lecture. And if you want to include this multi-antenna LO generation, like frequency synthesis generation and distribution, then that requires more than an hour of lecture. So in order to make sure that I confine myself within 1 hour, I just go through the basics of frequency generation, synthesis, and radiation. I'd like to also mention that I build my way out of basic concepts. And toward the end of the presentation, you will see a flavor of the use of electromagnetics and physics directly in integrated circuits, and the holistic design of radiators and oscillators toward the end of this presentation.
Dr. Heydari, just a brief pause there. Just wanted to mention to our viewers, I've had to disable the chat because of the problem we were having earlier. So if you have questions, just email them to me from the confirmation email you must have received from me, or from the invitation to attend earlier. So just email them to me, and I will take breaks every 15-20 minutes or so to answer your questions. Okay.
Okay, sounds good. Just a brief overview of what is really considered to be a millimeter wave frequency range. A number of applications have been unfolded as a result of this huge amount of activities in millimeter wave frequency range. Of course, you're familiar with 5G frequency range from 26 to 30 gigahertz. Of course, there is another frequency range within the 5G domain at around 38 gigahertz. Then we have the 60 gigahertz frequency range that is primarily used for gigabit per second HT, wireless HT, frequency range from 77 to 81 gigahertz, designated for automotive radars, and the W-band frequency covering the passive imaging primarily. And then going toward beyond 100 gigahertz frequency, which is something that people in 5G community is discussing right now. There is a frequency range from around 115 gigahertz to 240 gigahertz that is used for, can be used for broadband wireless communication and also high resolution imaging. And the high end of the millimeter wave frequency, which is really kind of the lower end of the terahertz band from 0.3 to 3 terahertz, which is more or less dedicated for terahertz imaging and spectroscopy. Now, essential in the design of primarily communication circuits and imaging systems is the notion of frequency synthesizer, which is used for LO generation and local oscillator generation, as you see, and also for source generation. So as you can see here, the whole notion of the source generation is very important for a wide range of applications. So in this presentation, I'm going to go through the oscillator design at millimeter wave. I will discuss frequency tuning, in particular inductive tuning, and I make a strong case in favor of inductive tuning versus in comparison with varactor tuning at millimeter wave frequency. Then I turn my attention to the discussion of a fundamental frequency PLL-based synthesizer, and then I will discuss a very exciting research on multiport circularly polarized resonator and radiator. This part of the presentation, this part requires great deal of, as I said, description of or borrowing concepts from the electromagnetic theory, and I do my best to make it simpler so that everyone understands what's going on. First, oscillator design at millimeter wave. So the challenges in millimeter wave frequency generation and synthesis are quite familiar with everyone. I list a number of important design challenges. Of course, at high frequencies, being able to generate sustainable oscillations that can also have high output power is challenging. Like lower frequency oscillators, phase noise is always a very important design parameter. And then depending on the application, the tuning range could be very wide. For example, if you think about like spectroscopy applications, then there is a need for an oscillator that can cover multi gigahertz of frequency range. And as the operation frequency approaches close to the maximum oscillation frequency that we call Fmax, then achieving low phase noise, high output power oscillation is very difficult. Adding to this is the severe loss due to the low quality factor and a small Cmax over Cmin ratio that contributes to a dismal tuning range at very high frequencies. So these challenges become much more pronounced at very high frequencies, and then we have to find ways or circuit techniques, system techniques in order to kind of mitigate these problems. Okay, so I would like to really start with the basics of the sinusoidal oscillator. We know that shown here is kind of a general system block diagram that is used, and we are familiar to kind of describe the oscillator using the concept of feedback. So an oscillator can be considered a closed loop feedback system. In particular, is a positive feedback system. And why we are using a positive feedback system in order to produce sustainable oscillation, because the basic requirement for a sinusoidal oscillator is comprised of two parts: a pair of small signal complex conjugate right half plane poles, which determine the oscillation frequency, and a mechanism for moving these poles toward imaginary axis as the envelope of the output waveform increases. So the first requirement, namely having a pair of right half plane pole, is really realizable using this positive feedback network. And then hopefully using the active devices that are used in, let me go to the pointer. So using the active device here, realizing this H of S, then the gain control mechanism can be conceived that can control the envelope of the output waveform as the oscillation amplitude grows. Now, the next question is that what kind of characteristic H of S should have inside this feedback loop in order to satisfy these two conditions? And without going through the details, we know that if the loop gain, in this case, since we are looking at unity gain feedback, the loop gain is equal to the open loop system, is if the open loop transfer function, or the loop gain in this case, have a pair of two poles, a pair of poles and 1, 0, then sinusoidal oscillation, once this system with this 1, 0 and 2 poles are placed within the positive feedback loop, then the circuit can oscillate. One particular example would be a pair of complex conjugate left half plane pole within that H of S, and an H of S with this complex conjugate left half plane pole and the 0, its transfer function or frequency response is given here. And if we look at the root locus of the closed loop transfer function, we know that according to the root locus of the transfer function, the closed loop poles are always starting at the location, at the initial location of the open loop poles. And the root locus, as we know, shows the trajectory of the poles and zeros as the gain will increase. Now, as we increase the gain, you see that this pair of poles are gravitated around the center of gravity, and the center of gravity here is the 0 of this transfer function, and they are basically taking a circular trajectory around this center of gravity, which is really the 0 at the origin, in order to get, as the gain increases, they emerge together, and then as with a further increase of the gain, one of these poles will be approaching the 0, the other one goes to infinity. But as you can see, at certain values of the gain, this complex conjugate closed loop poles will fall in the right half plane, and as a result, then the condition for oscillation will be satisfied. Now, rewriting this transfer function into another frequency response and then applying this famous Barkhausen criteria, we can calculate the minimum required gain for oscillation and oscillation frequency. And according to the Barkhausen criteria, if the imaginary part of the loop gain is becoming 0 and its real part is 1, then we can calculate oscillation frequency and the minimum required gain, which for this special case, the oscillation frequency is equal to the natural frequency of this system, the loop gain, and the minimum required gain is 1 over QT, where QT is related to obviously natural frequency and the damping factor alpha. Now, how to realize this system? Of course, one very straightforward circuitry with this transfer function is an RLC circuit. And we know that a parallel RLC circuit driven by a current source can have a driving point impedance whose characteristic or whose closed-form expression is shown here. And as you can see, we have a 0 and a pair of complex conjugate pole. And the next question is that how can we then realize this positive feedback, right? Now that we have H of S, and one example of H of S is this parallel RLC tank circuit, then the next question is how can we really implement this positive feedback network? And the answer to this question is also very straightforward. We know that one way of implementing this unity gain positive feedback loop is by using a voltage controlled current source here. In other words, replacing this current source, independent current source, driving this parallel RLC tank circuit with a voltage dependent current source here. And this voltage dependent current source is basically, as I said, implementing this positive feedback loop in a way that the voltage across the resistor sitting in the secondary side of this ideal transformer is sampled and is taken here, and this voltage is impacting the current, and the current is obviously coming back and create the voltage on the primary side of the transformer, and then you establish this loop, right? So the next question is then what kind of component can possibly realize this voltage dependent current source? And of course, we know what the answer is. One single transistor can single-handedly realize this voltage dependent current source here. So again, we started from the system level description of an oscillator using a positive feedback loop. We kind of found or synthesized a circuit that can possibly replace H of S, which is that this RLC circuit. And then to implement or realize this positive feedback, we use a voltage dependent current source here. And we said that, of course, a voltage dependent current source can be represented or modeled using a single transistor. Now, from here, if I want to replace this voltage dependent current source with a transistor, I arrive at this circuitry where we have the transistor. This transistor is indeed acting like a voltage dependent current source, where the current source is feeding the current to this parallel RLC tank circuit. The transformer is placed here, and then the secondary side of the transformer is coming back and is AC coupled to this the input source of the transistor. And of course, from the input source of the transistor, you see a 1 over GM, which is placed at the secondary side of this transformer. Now, of course, there is one way of implementing this circuit. Another way of implementing this circuit or this so-called oscillator is by replacing this transformer with the so-called tapped capacitor networks shown here. And it is proven that this tapped capacitor network can effectively behave like a transformer. And suffice to say that then a circuit that has this circuit model is shown here. With this transistor, as I said, we replace this transformer with this tapped capacitor resonator here. The voltage is again sampled at the output. The output is taken at the drain of this transistor. The output is sampled by this tapped capacitor resonator, is fed back to the input, and then the voltage controlled current source takes care of this feedback and then injecting current to this RLC tank circuit. So without going through the details, as I said, the tapped capacitor resonator, again, can act reliably like a transformer. The minimum required transconductance for this circuit to oscillate is shown here. The oscillation frequency is equal to 1 over square root of L-P times the series combination of these two transistors, which is shown here. Okay, so this is called a Colpi's oscillator, obviously. Another very widely used oscillator is what we call CrossCopper Oscillator. But how can we implement the CrossCopper Oscillator using the concept that we just started with? Again, we start with this positive feedback, unity gain positive feedback, and in place of H of S is this couple of single-tuned common source amplifiers in the feedback configuration. So in other words, H of S is replaced by these two common source single-tuned amplifiers in cascade. Now, redrawing this circuit will lead us to the famous CrossCopper pair oscillator. And we know that for this CrossCopper pair oscillator, obviously these two nodes are oscillating differentially, producing differential voltage, and the minimum required gain for oscillation is easily obtained. In fact, the minimum transconductance is equal to 1 over the resistor, or the conductance of this transistor, the loss of the inductor, and the oscillation frequency is simply obtained by the resonant frequency of each RLC tank circuit, assuming that these LC tank circuits are identically matched. Okay, so, but you know, the presentation here is revolving around millimeter wave, right? So the question is that, can I use this CrossCopper pair LC oscillator at high side of the millimeter wave frequency range? Let's assume that I want to design this, redesign or consider this LC oscillator for frequencies around like 150 gigahertz, close to Fmax, possibly above half Fmax. Can I use this simple CrossCopper pair for those frequencies? In order to answer the question, let's first look at the driving point impedance of this CrossCopper pair. And to understand and appreciate what is going on, of course, we can use a small signal model. And the small signal model of this CrossCopper pair is shown here. Without going through the details, the driving point admittance contributed by this CrossCopper pair is shown here. And the real part of this transconductance, ignoring channel length modulation, is minus gm/2, whereas its reactive part is totally capacitive. And in fact, this capacitor could be very big. If you look at it, CGD, the overlap gain to drain capacitance, contributes quite significantly to overall capacitance. That might not be a good news for FinFET technologies, for example, where CGD constitutes a big proportion of the overall capacitance. And therefore, it means that if this oscillator is going to be used at very high frequencies, and also if you want to design this LC oscillator at very high frequencies using advanced FinFET technology, then we are running into some problem when it comes to parasitics. Not only that, but also the driving point conductance of this circuit, which is roughly equal to minus gm/2, cannot be made sufficiently large to compensate for large losses at millimeter wave frequencies. What are those losses? For example, a skin effect dependent loss of the inductor, the loss of the capacitors. And all these losses, which by the way, get exacerbated at very high frequencies, cannot be simply compensated for by minus gm/2. And aside from this, the transconductance of the transistor at very high frequencies is also degraded. So we have to find a way to empower this transconductance, to have to find a way to, in fact, increase the negative conductance being used to compensate for the existing loss of the circuit. So what are the ways to do that? Of course, there might be many possible ways to do that, but one interesting way that I would like to share with you is shown here. So in order to kind of improve the negative conductance or increase the negative conductance at very high frequencies, one possible idea is to interject negative resistor as the source degeneration load of this CrossCopper pair, right? So let's then go through the circuit and study the circuit and find out how this pair of source degenerated negative resistors are helping this CrossCopper pair to increase the effective transconductance. So I would like to kind of, again, go back to this circuit, again, source degenerated negative resistor. If we try to derive the real part of input impedance, input admittance of this circuit, you see that the real part is equal to minus gm of this transistor pair over 2 times 1 minus gmRs. And obviously, depending on the bias current and the resistance value, we can make this, in fact, larger than the absolute value of this, much larger than gm/2. In fact, we can create a more negative conductance using this circuit. But of course, there is no such negative conductance in practice. We have to find a device that can replace or can realize this negative conductance. And as you can guess, a negative conductance can be realized using a transistor. When we talk about transistor, immediately we have to include the parasitic capacitors. So therefore, a more realistic component which should be placed as the source degeneration load of this cross-couple pair is comprised of this parallel RC circuit, where these capacitors are modeling the parasitic capacitance of the device. And if we put as soon as we put the capacitor here, then we see that the maximum operation frequency of this cross-couple pair is degraded by these capacitors because we are kind of adding more parasitic capacitor to the device. Now, to mitigate this, one way is to add an inductor to partially resonate out the capacitors. And if we do that, then possibly we can maintain the maximum oscillation frequency of this cross-couple pair. Now, we basically took halfway through the full circuit visualization of this circuit. From here, you can guess that a circuit, a composite cell that can replace this parallel RC circuit here is another cross-couple pair that is that can be placed underneath the main core cross-couple pair with that inductor that is used to partially resonate out the effect of the capacitors. So the full circuit, which we called double cross-couple pair topology is shown here, where we have the inductor again. These inductors are used again to partially resonate out the capacitor sitting here and here. And then we have our core cross-couple pair. And this circuit with this VCO, and in fact, this is a VCO, was designed for our 210 gigahertz fundamental frequency transmitter. And the phase noise of this oscillator was around minus 82 dBm per hertz at 1 megahertz offset. For more information, interested viewers can take a look at our paper, which was published in Journal of Solid-State Circuit, March 2014, which was an extension of an ISSCC paper in 2013, which was presented. And you can kind of go through, in this paper, great details have been spent to describe the operation of this circuit. So one way of then improving perhaps the operation of the oscillator at very high frequencies is to increase the negative conductance. And one way of increasing negative conductance is shown here. Now, when it comes to the frequency tuning, which is another performance metric for oscillator, we have to keep in mind that the basic oscillators, the way that the basic VCO, LC VCOs we learn is primarily based on the varactor. And let's kind of start by stating a very important fact here. Parasitic capacitors dominate the total capacitance and degrade the tuning range of the oscillators with varactor tuning. Even more importantly, varactors at high frequencies have low quality factors. In fact, a typical varactor at frequencies above 100 gigahertz can have a quality factor around 2 to 5. Compared to, for example, the quality factor of an inductor at this frequency, which could be as high as 20. So if then the message here is that absence of any kind of loss compensation mechanism, if we use a varactor-based LC-VCOs at very high frequencies, then we are running into the problem of not having a sufficient output power and excessively high phase noise for this oscillator. So then what can we do about this? How can we resolve this fundamental problem? In this presentation, I'm going to go through two effective techniques. One is varactor loss compensation mechanism or techniques, which I'm going to explain later on. But immediately right now, I'm going to discuss another technique in order to introduce tuning, which is that rather than kind of having capacitor as varying with the voltage, let's assume that the inductor is a component that is dependent on a current. By changing the current, we change the inductor, and as a result, we can vary the oscillation frequency. In other words, rather than having a varactor-based tuning, let's look at the inductive tuning, and let's look at the pros and cons of an inductive tuning. I would like to make a case that perhaps inductive tuning at high frequencies, very high frequencies, close to beyond 100 gigahertz, might be a better circuit candidate compared to varactor-based tuning. But why? So as we know that it is obviously a fact that as oscillation frequency increases towards sub-terahertz band, the inductor size will decrease almost quadratically. So, for example, 100 gigahertz center frequency, oscillation frequency for an LC oscillator oscillating at an oscillation frequency of around like 100 gigahertz or above can have an inductor as small as few hundred picohenry. And the Q factors as high as 15 to 20 for a small size inductor as much as few hundreds of picohenry is quite possible in silicon technologies. Another important notion here is that not only the inductor sizes become smaller, and the quality factor of these small size inductor are good, around like 15 and 20 inside silicon technologies for a monolithic inductor. Then another important fact here is that magnetic coupling between two mutually coupled inductors with coupling coefficient of 0.6 or more can be achieved inside the silicon. So I'm using these two important notions in order to kind of make my way out to implement or realize an inductive tuning mechanism for an LC oscillator. So how can I do that? So I would like to draw your attention to this particular circuit. This circuit is very simple circuit. By the way, I'm using an HBT, a pair of HBT. You can easily use a pair of CMOS transistors, so CMOS devices, doesn't matter. So we have a transistor, and this transistor at its gate, or the base in this case, we have a parallel RL circuit. Both sides of these circuits are terminated, at least the input, to a series RL, the series RL circuit, and the emitters are biased using this tail current. So why am I using this or employing this R and L at the base terminal of this transistor? Let's go back to our basic knowledge of electronic circuits. We know that, first of all, adding an inductor in series with the base terminal of this HBT or a gate terminal of a MOS transistor can introduce a negative resistance. On the other hand, adding a resistor at the base terminal of a transistor or a gate of a MOS transistor can introduce inductance, active inductance. This is what we call active inductance. And good news here is that this resistor, together with this transistor, introduces a current-dependent active inductor. So I'm using these two important observations together, hand in hand together, to implement a high quality factor active inductor. Why do I say high quality factor active inductor? Because again, this resistor together with the transistor is used to realize an active inductor, and the inductor itself in series with the gate or base is used to introduce negative resistor. So you can imagine that if there is a loss or the resistor in our circuit model, that resistor is possibly compensated partially by a negative resistor contributed by the inductor. And as you can see, these equations clearly show that, for example, when it comes to the negative resistor, LBB, this term introduces a negative resistance, and we can adjust LBB such that the negative conductance, the real part of Z in becomes very small. And also here, if you look at it, GM34, this term is directly contributing, and so is this term, is directly contributing to the active inductance. And by changing the current, likewise, by changing the transconductance, I can change the inductor. Now, shown here are simulated examples of what kind of tuning I can get out of this active inductor. This active inductor for at resonant frequency of 100 gigahertz for a series inductance of 60 picohenry for 3 different values of series resistor. We can see that as we change the current, the inductor is changing rather substantially. And the quality factor, interestingly, as the current increases, the quality factor increases. And we can see that this quality factor will increase further as we increase our LBB, as we increase the series inductor, simply because the series inductor, as I mentioned, introduces a negative resistor here. And that negative resistor compensates for existing losses, thereby increasing or improving the quality factor. Okay, so this core part of the circuit that I'm showing here, here and here, are responsible for current variant inductance, right, or active inductance. Now, how can I use this active inductance in my oscillator, right? In order to do this, I use the notion of magnetic coupling to couple whatever inductor I have here and here, whatever inductance active inductance, variable active inductance that I can generate using this pair of circuit, composite cell, and magnetically couple it to the core oscillator. And in order to do this, I'm using a transformer in order to couple the effect of the primary side of the transformer to the secondary side. Unfortunately, by adding this magnetic coupling mechanism to couple or induce inductive coupling to the core oscillator, which I haven't shown here yet, the variable inductor, the tuning range of the inductance obviously is compromised, because then there is a constant inductor which is effectively added to this variable inductor, thereby reducing the tuning range. But again, still the tuning range is there. We can achieve like 4 to 5% tuning range at very high frequencies. Now, putting this all this together, shown here is the complete example of a voltage control oscillator, varactorless voltage control oscillator with inductive tuning. On the sides, you see this pair that I used here, T3 and T4, with this RL base degeneration load that are responsible to produce active inductance. The active inductance using this transformer coupling is directly coupled to the main inductor, and shown in the middle is a differential clap, or you can say Colpice, modified Colpice oscillator. And the main oscillation frequency is obviously determined using this pair and this pair. And in order to further increase the frequency, I put together this VCO in a push-push configuration, meaning that I basically take this side and short wire them together, and then get this oscillation from this node. And as we can see, using a push-push configuration, I can achieve twice the frequency of the oscillation, or I can acquire twice the oscillation frequency of the core oscillator. So again, we are basically using this active inductance in order to introduce the inductive tuning. We are basically using a magnetic coupling to induce this active inductance or variable inductance directly to the core oscillator. And then we are using a clap oscillator in order to design my oscillator, and I'm using a push-push configuration in order to emphasize or extract the second harmonic. This oscillator, by the way, was designated for a frequency of 200 gigahertz, 0.2 terahertz, and in fact, the chip was fabricated. In this presentation, I'm not going to show measurement results per se, because this presentation, this seminar is intended for education, but just in order to prove my case that, in fact, using only inductive tuning without any varactor, how can we achieve tuning range? The measurement results at least show a 3.5% tuning range from 198 to 205 gigahertz, with a very good phase noise of around minus 86 dBc per hertz at 1 megahertz offset, and with a very good power efficiency. And this basically, and then as you can see, the output power remains constant, almost constant across the tuning range, which is one of the another positive attribute of this circuit. So far we discussed the inductive tuning as one way of mitigating the problem that we have regarding varactor tuning. Now, imagine that then, inductive tuning is obviously one way. Another way is just go back to the varactor tuning and try to find out some kind of loss compensation mechanism in order to compensate for existing loss of the varactor. And in order to appreciate how we can do this, let's go back to our original CrossCopper Oscillator, which is employing a pair of MOS varactors here. And here I'm basically using, at least ideally, I would like to use a loss compensation mechanism producing negative resistor, and this negative resistor possibly compensate for existing loss of this varactor. Okay, so the varactor's Q is obviously too low at very high frequencies, and we would like to see what kind of loss compensation network I can use, like this, for example, ideally, or in abstract mode, in order to compensate for the loss of the varactor. But unfortunately, there are a number of problems. Negative resistor is all, when we talk about negative resistor, always what immediately comes to mind is transistor as an active device. So if I want to use a transistor to implement a negative resistor, another problem comes to the picture, which is the existence of all these parasitic capacitor, and in fact, the loss associated with the transistor and what have you. So the parasitic capacitors associated with the loss compensation network degrade the tuning range. So therefore, it defies the very the very intention that we had. We wanted to increase the tuning range. We want to improve also the phase noise. But as a result of using this loss compensation mechanism, because of the existing parasitics, the phase noise and the tuning range will be degraded. So what can we do about this? Consider this. How about placing this loss compensation mechanism away from the node of interest? What are the node of interest? The node of interest is perhaps the output terminal for which we want to get oscillation. What do I mean by that? I mean, for example, still use this loss compensation network, but place it somewhere else. Of course, in this very simple CrossCopper Oscillator, we cannot think of any other place but this place in order to do the loss compensation mechanism, to provide or to insert this loss compensation network. But let's kind of look at a more complicated circuit. Imagine that we have a ring oscillator, and shown here, for example, a 4-stage ring oscillator. I'm showing it here. If you follow my laser pointer, you see that there is this ring oscillator. And this ring oscillator has a varactor here. So we have 4 varactors connected to the input of each delay stage. And then I'm also inserting a loss compensation network right in parallel with this varactor. So this is my main ring oscillator. So the main ring possibly oscillates at ω0. But what I'm going to do here is that since each delay stage incorporates a transistor, and the transistor is a nonlinear device, what I can do is that I can basically take a harmonic of this transistor. In this case, for example, in this particular case, since we are looking at a 4-stage ring, I'm interested in extracting the 4th harmonic of this oscillation circuit, oscillation waveform. So the transistor extracting the 4th harmonic here, 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 and here, and guiding this 4th harmonic to the common node, and observe this node as the node of interest. So if I do that, then possibly, and if I use, for example, some notch filters or traps placed at nth of frequency, I basically disallow this nth harmonic, in this case 4th harmonic, I disallow or prevent the 4th harmonic to inject back to the main loop. So the main loop is oscillating at ω0. I'm creating 4th harmonic using the nonlinearity of the devices inside these delay stages. And then I guide these nonlinear harmonics, in this case, in this particular case, for example, 4th harmonic, to a common node, extract the oscillation here at 4th the frequency, 4 times the frequency. And then yet I try to protect the node here, the oscillation here, from parasitics of the oscillator. So for example, if we want to design a 200 gigahertz frequency, I can design this oscillation, the main oscillator, to be oscillating at 50 gigahertz frequency. I can introduce a loss compensation mechanism right in parallel with this varactor, not worrying about affecting the main oscillation, because the main oscillation would be at 4th harmonic at 200 gigahertz, and this 200 gigahertz is derived from here. So this is one way of doing this. And in fact, I'm one example, another realistic example of doing this is shown here. So shown here, rather than having like 4-stage ring, consider a 3-stage ring oscillator. So we have a 3-stage ring oscillator, 1, 2, 3, 1, 2, and 3. And then we are using our varactor, but this varactor is, I call it an active varactor. So we have an active varactor here, here, and here, sitting at the input node, very similar to this one. Imagine that each delay stage here is replaced by a single transistor. So I had my varactor here. So I have my active varactor sitting here, here, and here. And then this oscillator, which is basically this loop, is oscillating at a fundamental frequency. And I take 3rd harmonic, extract the 3rd harmonic. I guide the 3rd harmonic of these transistors up using these branches, and also using the filters here, preventing the 3rd harmonic to leak back to the main loop. And then by guiding this 3rd harmonic, all these 3rd harmonics will be emerging at this node, and then I will be able to get the 3rd harmonic. Now, the question is that, how can I design this active varactor? And one way of designing the active varactor is shown here, what I call a Colpitts-based active varactor. So we have the active varactor here. We have a Colpitts device. We know that from the input of the Colpitts device, we see a capacitor here, and a negative resistor. So I basically realize the negative resistor using this Colpitts-based or clap-based composite cell, and also put the varactor as part of the tapped capacitor resonator of this Colpitts cell in order to introduce tuning. By the way, we use this Colpitts-based active varactor inside this ring VCO as part of our frequency 300 gigahertz frequency synthesizer, which I'm going to explain next. So far we discussed design challenges in oscillators at millimeter wave frequencies. We at least introduced one candidate that can work at very high frequencies. I went through inductive tuning as an alternative mechanism for tuning at high frequencies. I also introduced an effective loss compensation mechanism that compensates for the varactor loss. Now I'm kind of discussing, or I'm going through a millimeter wave fundamental frequency PLL-based frequency synthesizer that uses this technique, in particular, for example, an LCVCO with loss compensation mechanism in order to produce oscillation at very high frequencies.
So, excuse me, Professor, we have a couple of questions. Would this be a good point to cover them?
Absolutely.
Sure. Venkata, you had a couple of questions lined up. I think I have unmuted you. You should be able to ask.
Yeah. Hi, Professor. I was wondering, could you talk about the robustness of these topologies, the oscillator topologies, and talk about how their performance is varying over PVT?
Mm-hmm. So PVT is an issue always, but PVT is always an issue for any circuits. Of course, the circuit techniques that I introduce here are not an exception. The PVT variation is partially captured by the tuning range of the VCO. So if I can have relatively good tuning range for the VCO, I can somehow capture the PVT of the VCO, particularly if the VCO is going to be used for a PLL. So therefore, the PVT is not really worse than, for example, a conventional VCO, and the techniques that are used in order to capture the PVT variation are almost the same as what we use in the high frequencies. Namely, for example, you have a wide enough tuning range to capture the PVT. When it comes to the robustness is perhaps can be defined in the context of VCO as the phase noise, for example, right? Or being able to introduce, to generate high enough output power. So the phase noise, at least these techniques, I showed that inductive tuning, since the inductive tuning uses inductors, and inductors at high frequencies have higher Q compared to varactor counterparts, then naturally the phase noise that you can get out of the inductively tuned LCVCO is better. And that means that if the robustness is defined in the context of low phase noise, then of course one can argue that inductively tuned LCVCO can outperform a varactor-based LCVCO at high frequencies. When I say high frequency, I would say above 100 gigahertz near max frequency. Yes.
Yeah, got it.
Other questions? Okay, so here I would like to kind of go through a design of a fundamental frequency integer n frequency synthesizer that we designed several years ago. And I'm going to go through a number of techniques that we use in this phase lock loop to achieve a 300 gigahertz frequency. In fact, I want to show that in silicon technologies, it is in fact possible to design relatively low phase noise, high performance PLL with relatively good output power in silicon technologies using some novel circuit techniques. So the loop of the PLL is shown here. As I said, it's an integer n PLL. The synthesizer employs a third order loop filter, a triple push VCO, which I already introduced, but I'm going to go through this a little bit more. And then we have a divide by 4 frequency divider here. And this divide by 4 frequency divider is co-designed and co-optimized with the VCO. And I will explain what do I mean by co-optimizing this divider together with this VCO. I'm going to explain more. The co-optimization and co-design, as you will see, will be done at both the circuit design level and the layout level. And then at the output of this divide by 4 frequency, we have this our famous divider chain that divide the frequency all the way down to lower frequency. So overall, we wanted to do a divide by 1024 in order to bring down the frequency to the crystal oscillator that we use as an off-chip signal source for this frequency synthesizer. So the fundamental frequency of the VCO is 300 gigahertz. I'm using third harmonic within this VCO in order to synthesize a 300 gigahertz frequency. And as you can see, I'm using a 3-phase injection. Look at this, a 3-phase injection in order to connect the VCO to the next subsequent divide by 4 frequency divider. Okay, so in order to increase the output power, we are using a technique that has been used by the prior work in order to achieve the maximum output power. It was shown by the prior work that if we consider a device here, like for example, a transistor, and you try to kind of calculate or derive the overall power, the reactive power here, PG, is dependent on the forward gain and the reverse gain, as you can see, and its phase. So what it means here is that the power, the reactive power here, depending on the phase shift of this Y12 plus Y21 of this 2-port network can vary, right? And this optimum phase, in other words, there is an optimum phase shift that can lead to the maximum PG. So what does it mean? It means that if I want to get the maximum output power out of a single device, I have to make sure that there is a certain phase relationship between the input, for example, in this case, base, and the output, in this case, collector of this device. And if there is a certain phase shift, then I can achieve the maximum output power for this single device. So this is really a knowledge that was gained by a prior work paper published in Journal of Solid-State Circuit 2011. We are using this kind of notion in order to design a high power ring oscillator. So remember that we want to design a 300 gigahertz ring oscillator, and one way of achieving this 300 gigahertz oscillation is, as I said, by designing the oscillator at lower frequencies and using a higher harmonic in order to achieve a 300 gigahertz frequency. For example, three candidates come to mind. The first candidate is comprising a 2-stage ring. The second candidate is comprising the 3-stage ring, and the third candidate is using a 4-stage ring. And if you notice, in case you notice, I'm also intentionally using a series phase shift between the output of one stage to the next. Okay, so if you want to use a 2-stage ring in order to design 300 gigahertz frequency, this 2-stage ring can be operating as a push-push oscillator, right? In other words, I can get the common node here, and a strong second harmonic can appear here, and I can basically extract the second harmonic in order to achieve 300 gigahertz. And if that's the case, then this fundamental 2-stage ring oscillator should be designed to oscillate at 150 gigahertz frequency. Okay, and in order to achieve the maximum output power, let's go back here at 150 gigahertz frequency. If I'm using this device at 150 gigahertz frequency, in order to achieve the maximum output power, get the maximum output power out of one single device, the required phase shift should be around 115 degrees, right? So 150 degrees excess phase shift from the input to output of each transistor is needed in order to achieve the maximum output power. If I'm using 3-stage ring, of course, the main ring should oscillate at 100 gigahertz. In this case, again, if you go back and look at 100 gigahertz, at 100 gigahertz, the excess phase shift required to get maximum output power is around 130 degrees. And also so on and so forth. Like, for example, for 4-stage, the main ring core should oscillate at 75 gigahertz, and the phase shift should be, excess phase shift is around 145 degrees. But again, as without using this excess phase shift, of course, we know that the phase shift from input to output is around 180 degrees, right? So therefore, to achieve the 115 degrees optimum phase shift, we have to introduce yet additional 65 degrees in order to make sure that the phase shift between these two is remaining at 115 degrees, right? Likewise here, so for a 3-stage ring, the oscillation frequency, the phase shift, normally in the absence of this theta, the phase shift between input and output of the device is around 120 degrees. Here, the optimum phase shift is 130 degrees. So we require to have additional 10-degree phase shift in order to get to this optimum phase shift. And this 10 degrees is realized using these excess phase shifters that are placed between the output and input of each stage, and so on and so forth. So, but if you compare these three candidates, of course, it seems that the three-stage ring would be a more viable candidate for this 300 gigahertz oscillator, simply because the excess phase shift required in this here as part of the ring oscillator is less. And obviously, the lower phase shift means that the loss of the components, passive components used to realize this excess phase shift would be less. So we ended up using a three-stage ring in order to achieve this 300 gigahertz frequency. And that basically takes us to this oscillator circuit that I already explained. So we have a three-stage ring oscillator, as I mentioned. You're using this Colpitts-based active varactor with loss compensation mechanism inside it in order to create or introduce tuning, yet be able to compensate for the loss of the varactor. And again, I would like to remind you that this main ring oscillator is oscillating at 100 gigahertz frequency. So the third harmonic is guided to the output, is emerging here at the common node, producing this 300 gigahertz frequency. Now, in order to disallow the third harmonic to go back and leak back to the main ring stage, we basically try to design the circuit such that the whole circuit here, the whole passive circuit from the output of each stage to the input of the next stage, acts like a notch or trap filter at the third harmonic. So in other words, at the third harmonic, this node is short, disallowing the third harmonic to revolving around the loop. So the third harmonic finds no way but to go up and emerge at this node in order to produce the third harmonic. So this is a trick we use in order to guide the third harmonic only up and disallowing the third harmonic to go back to the main ring. So the divider loop also is very interesting. We are using a three-phase divider loop with multi-injection in order to kind of design this divide by 4 frequency divider. So the principle is very simple. We are using 3 injection, like a 3-phase locking injection, as part of a ring, another ring, in order to design a divider loop. I'm not going to go through the details because it is very straightforward. And one way of designing this injection lock frequency divider is shown here. So again, the inputs are coming from the inputs B1, B2, and B3 are coming from the oscillator. B1, B2, and B3 are coming from the output of the Colpitts-based active varactor of the main oscillator injected to the input of the transistor. The transistor produces the the 1/4 of the harmonic. The 1/4 will be flowing through the main loop, and also the same thing. We want to make sure that the third harmonic doesn't go back to the main loop, and as a result, by using this technique, by using this circuit, we can produce or we can design a multi-injection divide by 4 frequency divider. For more information about the circuit operation, I would like to refer you to our Journal of Solid-State Circuit, which was published in 2014. Now,
Professor, can we take another break? I think we have a few more questions, but before we go to the questions, just want to remind our participants, we had to disable the chat because of the trouble we were having earlier. So if you have any questions, just hit reply to the email that I sent from Eventbrite earlier, which had the links, the Zoom link for this meeting. So it says no reply, but then you can just hit reply to that email and it will send your questions to me. So if you have any questions, just reply to the email with the Zoom links that you received before the meeting. Venkata, you had, I think we have a few more questions, right? So go ahead.
Yeah, hi, Professor. So I'm wondering, when we go to advanced nodes, as the technology evolves and the gate length shrinks, I mean, what are the challenges in the oscillator design? Are you going to talk about those points as well?
Not really, but designing oscillators in advanced nodes, like for example, FinFET technologies. This presentation doesn't cover that, but if there's a specific question, I would be happy to answer the questions. If there's yes, go ahead.
The question is like, are there any limitations in terms of Like how many transistors can we stack, or
Exactly.
yeah.
So the main challenge is the parasitics and the fact that, for example, the gate drain overlap capacitance of the device is no longer a tiny portion of the overall parasitic capacitance. What does it mean? It means that, for example, if you want to design an LNA, if you want to design an oscillator, then you have to account for the CGD of the transistors. You cannot ignore it. And of course, for LNA, we know what happens. CGD for LNA may create some kind of conditional stability problem or instability problem. For the oscillators, it creates a drift from the main oscillation. And the drift, if it's not captured, then creates some problem. And also it adds to the phase noise degradation. So these are some of the things that most notably for in terms of parasitic capacitance and their impact on the oscillation frequency at high frequencies, and advanced CMOS technology can come to the picture. So in general, FinFET transistors, while they are very good for digital implementation, due to the fact that the parasitics at very high frequencies, particularly the unwanted parasitics, CGD, most notably, would be substantial compared to the overall capacitance, then that may create some problem for very high frequency oscillators in FinFET technologies.
Oh, got it. So the CGD is a problem. How about, like, as we advance through the technology, we have higher FT and Fmax, right? So that's an advantage in terms of the oscillation frequency, correct?
Not necessarily. This point is highly disputed. So the maximum oscillation frequency, operation frequency of the device, unfortunately, will not scale up with the same scaling factor as the device feature size. In other words, going from like 45 nanometer all the way to 7 nanometer, we cannot hope that the Fmax of the device all of a sudden goes to like 500, 600 gigahertz. In fact, the maximum operation frequency turns out to be saturated to around like 350 gigahertz for FinFET technology. What I'm trying to say here is that advanced processes are not really leading to outrageously higher Fmax of the device. And that's the problem. That's the reason that a number of techniques have been used, like, for example, using harmonics of the main oscillation frequency, like the way I just did it here, in order to design high frequency oscillation. Advanced technology nodes, in other words, cannot really help design fundamental frequency oscillators at very, very high frequencies, simply because the Fmax of the design of the process is not really scaled, unfortunately.
Got it. Thank you.
So we have a couple more questions from the email channel. So I think this next question has to do with one of your earlier slides. Doesn't large RBB greater than 20 ohms at the gates of the transistors significantly degrade the phase noise performance? And the second related question is, and if such a large RBB is in the signal path, then won't it kill the oscillation?
First of all, the RBB is not in the signal path. So look at this. RBB is away from the signal path. RBB is just used to introduce tuning, and the signal path is here. So the large RBB, there is a point about the phase noise. So let's analyze this, right? So large RBB. So RBB, in fact, introduces this active inductance, right? And also, if we increase RBB, it means that the noise of RBB, input referred noise of the RBB, will decrease. So it's not really clear if increasing, of course, you don't want to increase RBB to kilo ohm range. Look at the range of the values for RBB, 15 ohm, 20 ohm, 25 ohm, simply because we are using RBB to implement or realize that active inductance, right? Let's go back here. We are basically using this RBB in order to generate this active inductance here, right? Look at that. So therefore, if I'm not really using, if I increase RBB so much, then the active inductance value will increase. And that means that then the frequency of the oscillation, this is not really good for that desired oscillation frequency which we intend to use, right? So therefore, RBB should be chosen in regard to the relative inductance that we want to use here. Like, for example, for a 200 gigahertz frequency or 100 gigahertz core frequency, look at the effective inductor range that we are looking at, around like 80 picohenry all the way down to 40 picohenry. The inductance value is not that big because we are operating at very high frequencies. Therefore, RBB also accordingly should not be very big. And therefore, the phase noise contribution is not much, particularly if you consider that RBB is away from the signal path and doesn't contribute to the output power degradation.
Okay, next question has to do with the later slides. How sensitive are these architectures to the matching between all those passive components? I guess this has to do with the slide prior to the one that you're showing now. Yeah. Yeah, I guess the question is how sensitive is the architecture to the matching, considering all the passive components? Yeah.
Okay. So matching here, the way that we use matching here is to generate to satisfy a number of operations or operation functions that we intended for. Like for example, in this case, if you look at this LVB and this resistor, these two are used to realize that 10-degree phase shift. Remember this 10-degree phase shift that we need in order to arrive at the optimum phase shift for the maximum output power. So these inductors and capacitors in this particular ring stage oscillator are intended for acquiring the required excess phase shift, and also in this case, for example, creating a trap at third harmonic, right? So therefore, if you say matching circuit, you have to you have to be careful about this. So the matching circuit in this case is used for a particular purpose, to achieve a certain phase shift for the purpose of maximizing output power, and also to create some kind of filtering mechanism, like a trap at some certain frequency. And that itself is designed in a way to satisfy these two purposes for this particular case.
Okay, one more question. Can you please illustrate how we got 3FO by connecting the three inductors?
Mm-hmm. So we get the third harmonic. So the trick behind this 3FO is really lies on the nonlinearity of the transistor. The transistor third order nonlinearity is used to produce the third harmonic. Now the third harmonic is picked up by the inductors LC tuned at 300 gigahertz frequency. So LC, as I will show the layout and hopefully you will appreciate it. So LC length, the length of these microstrip lines are chosen together with the capacitors sitting at the output, for example, such that the so-called tank frequency, resonance frequency here and here and here are tuned at 300 gigahertz frequency. But the main culprit behind the third harmonic is really the nonlinearity of the transistor. So the nonlinearity of the transistor is mainly responsible to produce the third harmonic. But to extract it, of course, you have to make sure that LC length and the capacitance values are chosen such that they tune at 300 gigahertz frequency. If that's the question, I can elaborate more if there is a doubt here.
The speaker the audience member who asked the question, if that answers your question, fine. If not, just send me another email, okay, and we'll pass that on to the professor. I think it's very clear.
The third order nonlinearity is we use a transistor nonlinearity in order to produce the third harmonic, and the third harmonic is tuned using this LC and the capacitor here. But how can we adjust LC? Let's go back to the layout. So the layout is really kind of, you can say this is an art piece, honestly, to design the layout of this oscillator together with the divider. So remember at the beginning of this part of the presentation, I said we are co-optimizing or co-designing the oscillator together with the divider. So what I mean by co-designing and co-optimizing is shown here. So shown here, we can basically distinguish two possible loops. This loop that is indicated in like gray color, and then we have the inner loop, and we have this kind of middle node or a middle node here, which is supposed to extract the third harmonic, right? So the outer loop is responsible for realizing all these transmission lines that are used for the injection lock divide by 4 frequency divider. So this is the outer loop. And the resemblance of topology between the frequency divider, look at the frequency divider topology, and look at the oscillator topology. So they are in shape and topology, in topology are extremely similar. So I'm using this kind of topological similarity in order to design the layout such that I can basically kind of co-design these two together. Again, the outer loop together with the transistor realizes the frequency divider. The inner loop here is designing this three-stage ring oscillator. If you look at it, the output connecting this inner loop to the outer loop is this Colpitts space active varactor, Colpitts space active varactor here and here and here. And then the inner loop, look at this, there are definitely microstrip lines in the layout. And I didn't show the layout here. If you, I would like to refer you to the Journal of Solid-State Circuit paper. We have a blow-up version of the dye photo, and you can see that there are like 3 lines literally inside the chip that are coming out of the transistors. These lines here are chosen, the length of these lines are chosen such that together with the pad in the middle, they oscillate, or they resonate at 3f0. The main oscillation frequency, again, the length of the transmission line here, here, and here are chosen such that we achieve the required 10-degree excess phase shift that I earlier explained, and also required trap filter at the third harmonic. If you look at, again, for example, the varactor, the active varactors here, they are connecting the inner loop to the outer loop that is used for the divider. So in other words, the divide by 4 frequency divider shown here, the main 3-stage ring oscillator shown here are co-designed together and co-optimized. And if we do that, then it, according to our measurement, we were able to achieve very, very good phase noise and output power by co-designing everything holistically, the divide by 4 and the oscillator together holistically, and treat it as one single block in the layout to optimize the circuit performance. Okay, so I can stop here, guys, or I can continue. It depends on the time. The fourth topic that I'm going to talk about is kind of a little bit more sophisticated multi-port circularly polarized resonator. I would be more than happy to share with you the magnificent theory that my former student, Dr. Nazari, proposed and invented and explored. So it's an exciting topic. But given the time, I can stop right here, answer any questions that I have, that you guys have, or I can continue with the presentation.
So we are good on time, and this talk is being recorded for people to watch later. So if you're okay, then we're okay to continue.
Okay, so the fourth topic of this presentation uses a massive amount of knowledge of the EM theory and the physics in order to design a very exciting multi-port circularly polarized resonator and radiator. And this design was really kind of envisioned, implemented, and successfully conducted by my former student, Dr. Payam Nazari, who is right now a senior design engineer at Qualcomm. And I do my best to explain the bits and pieces behind this. You will appreciate the genius design behind this. So the design was presented in 2017 ISSCC, and later on was appeared in 2017 issue of Journal of Solid-State Circuit. Interested audience are referred to this paper, where we explain the fundamental theory of the multi-port oscillators. There is a great deal of theory behind this multi-port structure that I don't have time to go through, but I'm going to talk about some of the outcomes of this fundamental theory and leverage this fundamental theory in order to explain this cavity-backed, circularly polarized radiator that we designed and fabricated. So again, I'm going to discuss millimeter wave, circularly polarized, cavity-backed, multi-port resonator and radiator. First, I would like to start by laying out several strong cases in favor of circular wave polarization. The 2 figures of this slide indicate the rotation of an exemplary horn antenna around its normal axis and its impact on polarization loss factor, PLF, when it receives a linearly polarized EM wave on the left, or on the right when it receives a circularly polarized EM wave. To increase the signal-to-noise ratio in a line-of-sight wireless communication, we know that the radiation polarization of the transmitter and the receiver antennas must match one another for maximum detection gain. For linearly polarized antennas, this requires the accurate alignment between the transmitter and receiver antennas. Otherwise, the receiver antenna, as is shown here, cannot efficiently receive the transmitter signal to the extent that the detection gain can in fact significantly drop when the polarization of the transmitter and receiver are orthogonal. Look at here, 90 degrees and 270 degrees. Furthermore, for many applications, the transmitted EM wave is subject to random polarization shift. For example, due to a scattering after reflection from rough surfaces or propagation through an ionized medium, which is likely to happen in tissue imaging. On the other hand, circularly polarized waves are resilient to such polarization shifts and misalignments. A design approach, therefore, to co-design a high-power, low-phase noise oscillator that can produce a circularly polarized radiation is vital to achieve high radiated power and high DC to EIRP efficiency. So various oscillator topologies, as I mentioned in this presentation, have been examined to provide the optimum voltage gain condition for maximum power generation. While these approaches are able to extract the maximum RF power from a single active device at the frequency of interest, this output power is still far too low to be considered for millimeter wave radiators. To further boost the output power level, power combining schemes are normally used to combine the RF output powers of multiple oscillators, as is shown here. Primarily, this has been achieved by employing either an on-chip power combining network on the right side or multiple antenna elements for constructive power combining in free space, that what we call a special power combining, shown in the left side. In both methods, however, in addition to power combining networks, a coupling network is mandatory to ensure phase-lock oscillation of all constituent oscillator elements. These methods, however, require lossy passive or power-hungry active coupling networks, and in fact buffers to lock the oscillations together, thereby remarkably degrading DC to RF efficiency. So one question then arises, and this question is very fundamental. Is there a way to improve signal generation and radiation efficiency? To address the fundamental weaknesses of the existing power combining network that I just explained right now, we introduce a high efficiency and high power multiport element, which can concurrently perform a multitude of operations. It can concurrently operate as a resonator, as an antenna or radiator, and a power combiner, thereby avoiding the lossy coupling networks and antenna buffers. As a result, in our proposed technique, we can inherently create higher radiation power and efficiency. But the question is, can such a structure exist? Moreover, and most importantly, can such multiport structure with multifunction capability that I'm summarizing here is capable of generating circularly polarized radiation? So let's go through some of the design goals that we want to have. So we are seeking a multiport passive structure. Why? Because we want to have a multi-element signal generation in order to do the power combination. So in order to achieve this multi-element signal generation, we need to have a multiport structure. Also of particular interest is to generate circularly polarized radiation. And in order to do this, according to our study, we need to come up with structures with rotational symmetry. And I'm going to give you one example of a structure with rotational symmetry. The third design goal is that, of course, we want to have a high power and low phase noise. And in order to do this, the core resonator, which is used as part of our resonator slash radiator slash power combining, should exhibit high Q. And one structure, high Q structure, that is very familiar to microwave designers is called, obviously, microwave cavity resonator. The microwave cavity resonator, there is a closed metal structure that confines the EM energy that leads to high Q, high quality factor resonance compared to LC resonator. In fact, the dedicated microwave cavity resonator can achieve a quality factor by as much as 10 to the power of 6. Also, needless to say that the microwave cavity structures, independent, separate, dedicated microwave cavity structures, normally favor symmetric shapes, and that itself in turn lead to higher quality factor. Okay, as I explained, power-hungry millimeter wave antenna buffers and coupling networks degrade the overall efficiency. Therefore, a multiport radiator should be explored that can maximally extract the RF power from the active devices while providing proper excitation phases for circularly polarized radiation. In fact, as I'm showing here, if a rotationally symmetric structure is excited by distinct, evenly spaced phases of an RF signal, so that the overall phase rotation is 360 degrees, The resulting radiation will be circularly polarized, as shown here by this graphical presentation. So in our JSSC 2017 paper, we expanded the theory of multiport oscillator circuits with multiple active devices exciting a multiport passive structure. Due to the lack of time, unfortunately, I cannot go through the elegant theory of multiport rotationally symmetric oscillators. I would like to refer viewers to our paper published in 2017 Journal of Solid-State Circuit. Based on this theory, we introduced a novel on-chip octagonal waveguide cavity-backed structure that is shown here as part of this multiport radiating element. It is composed of 8 symmetric feed ports, 8 radiation slots on top of the plate, a hole at the center of the top plate, and I will discuss the purpose of all of these in the next couple of minutes. I will discuss also the cavity. The cavity is inherently high quality factor, and this is, by the way, an on-chip cavity. The structure of chip cavity is extensively discussed in the paper, but for viewers who are interested, I can go through the structure, how we laid out this cavity inside the silicon process. It's a very interesting structure, but inherently this cavity structure can exhibit high quality factor. And this high quality factor can be used to achieve high power and low phase noise resonance. 8 CPW feed lines or feed ports are placed on the periphery of this cavity and are connected to the top plate to excite it, enabling power combining capability within this multiport cavity structure. Oscillation is generated by an 8-section loop surrounding this cavity, where each section provides 2 stages of amplification. This cavity is also part of the resonant network. In fact, this cavity participates directly in determining the oscillation. The loop enforces 45-degree phase difference required for circularly polarized radiation between the cavity adjacent ports, and the cavity combines the power injected to its 8 peripheral ports and radiates a circularly polarized signal. Now, the question is, why a circularly polarized radiation is guaranteed here? In our paper, in fact, we have proved that a general theory stating that for an N-port passive radiating structure with rotational symmetry incorporating N rotationally symmetric radiating slots and feed ports, if the feed ports are excited by signals of equal magnitude and constant phase shift of 2 pi over N in general, such a structure will generate circularly polarized radiation along its axis of symmetry, which in this case is Z-axis here. By exciting the cavity with even space phases, shown here, the 8 symmetric slots on the top plate radiate a circularly polarized signal without any substrate leakage and the need for silicon lens. The length of the slots control the resonant frequency and thus the frequency of the peak radiation power. Now let's study the cavity excitation under the condition that lead to the steady-state oscillation. Under this circumstance, namely, in order to have sustainable steady-state oscillation, the port impedances, driving point impedances, looking at each port, should all be identical. Z in 1 equals Z in 2 equals Z in 3, all the way Z in 8, and I call it ZCM. So what is the relationship between these two port impedance, these port impedances and the Z parameters of the multiport structure? For a circularly polarized, a circularly symmetric network, we have proved that the port impedance, indicated as Z in K, is calculated as the circular convolution of Z parameters and the exponential Fourier basis functions e to the power of j m pi over n. In this case, m is replaced by n minus k. Of particular interest for the purpose of circularly polarized radiation of all the possible solutions. And in fact, we can prove that there are 8 distinct solutions. There is one solution that leads to the oscillation and also circularly polarized radiation. We have proved that this solution is achieved with a phase difference of pi over 4. So we have to achieve a phase difference of pi over 4. And for this case, if we simulate the driving point impedance of this multiport structure, you see that there are conceived two resonant frequencies can be conceived. Among the others that are located at higher frequencies and not shown in this figure, the higher resonant frequency at 116 gigahertz is chosen. to be the target oscillation frequency as it coincides with the oscillation of the maximum radiation gain. I'm not going to go through why this is the case, but it can be proven that the second resonant frequency coincides with the frequency of the maximum radiation gain, which is simulated to be around 1.25 dB. So the frequency response of the driving point impedance is modeled using a shunt parallel RLC tank circuit to gain some intuition about the intuition about the operation of the cavity and its impact on the oscillation and sensitivity of the oscillation. And figure shows that the frequency response of this model RLC circuit resembles the imaginary and the real part of the cavity structure. And as a result, using this parallel RLC tank circuit, we can somehow model the operation of the tank circuit. Look at the quality factor of the structure, which is 38 at 116 gigahertz frequency. In fact, this is a loaded quality factor, and it is a remarkable quality factor for people who are working at frequencies above 100 gigahertz. They appreciate this very high quality factor. So the loop here needs to provide sufficient loop gain, and the loop surrounding this cavity structure should be able to provide sufficient loop gain for sustainable oscillation, implying that its port impedance, which I call Y loop M here, Y loop M, which is identical for all ports due to the loop's rotational symmetry, needs to provide sufficient negative resistance to cancel the cavity loading impedance, ZCM. In other words, the overall admittance looking at each node should be summed up to 0. The admittance offered by this multi-port structure and an excitation network should be added up to 0 in order for this structure to oscillate. So as I said, not only we want to have oscillation, we want to have circularly polarized radiation. And to achieve the circularly polarized radiation, it turns out the phase difference between the adjacent nodes should be equal to 45 degrees. And in order to do this, we have to design the matching network of the surrounding circuit. So if you look at the surrounding circuit, is comprised of a two-stage amplification with matching circuit. And we design the matching circuit such that only at the phase shift of 45 degrees, the real part of the impedance, the overall impedance, is negative, and the imaginary part is equal to 0 for all other modes of operation. In other words, for all other phase shifts other than 45 degrees, we've designed this matching circuit such that the real part of the corresponding admittance is greater than 0. And as a result, the other modes do not have enough power to oscillate. It is observed that this cavity also exhibits a resonance at a frequency slightly lower than 116 gigahertz frequency. In fact, this corresponds to the mod oscillation frequency of 0, M0. This results in an unwanted in-phase oscillation around the cavity ports. Unfortunately, loop gain for this mode M equals 0 cannot be suppressed by matching network. So we have to find another way to kill the in-phase oscillation component. Now here comes this hole that my student created right in the middle of the top plate of the cavity. So by adding this hole, we are able to basically suppress the in-phase oscillation. And this hole basically kills the undesired in-phase oscillation, and therefore, if you use this, then we don't see any kind of close oscillation frequency or the resonance frequency at close to the desired frequency. Okay, so on the left side, the Smith chart has been shown, and simulated. Smith chart shows the simulated the Smith chart of the overall driving point admittance for different modes of oscillation. And as you can see, thanks to the specific design of the matching circuit of the surrounding multi-stage network, we are able to make sure that only for the phase shift of 45 degrees, the imaginary part of the driving point impedance is coming out of the Smith chart. For all the other phase shifts, we want to make sure that the real part is greater than 0. And as I said, all these circles will be coinciding or will be residing inside the Smith chart. And shown in the right-hand side is a simulation result that shows the real part and imaginary part of the driving point admittance at each port or port admittance. And as you can see, for a narrow range of frequencies around 115 gigahertz, we see a negative real part introduced by this multi-port structure.
Professor, would this be a good time to break for questions, or are we close to the end?
We are close to the end.
Okay.
Okay, so the design was this 114 gigahertz multi-port circularly polarized radiator is implemented in 130 nanometer SiGe by CMOS process. Shown in this slide is the die photo. The cavity with 1.5 millimeter diameter is seen at the center of the chip. The core radiator occupies an area of 2.4 by 2.4 square millimeter and consumes around 505 milliwatt of DC power. Also, the 8 symmetric radiation slots at the center hole responsible for suppressing the in-phase mode are visible in the die photo. So I'm not. I didn't include the measurement pattern, measurement setup or test setup of this experiment of this chip. The test setup itself is very complicated because we want to measure the circularly polarized radiation. But what we do here is that we are using a horn antenna on the receive side. Of course, it's a linearly polarized in order to measure the circular polarization mode of this radiator. To characterize the radiation pattern, the receive power was captured using a WR6 power detector, while receiver horn antenna was swept along the theta direction. So shown here is really the way that we rotate the horn antenna. So there is a theta phase shift here. So we have also other kind of phase differences that I'm going to explain in just a few minutes, okay? In just a few seconds. So the receiver antenna horn was swept along the theta direction in 2 orthogonal azimuthal planes, one at phi equals 0 plane and the other one phi equal 90 degrees. Since horn antenna polarization obviously was linear, whereas that of the radiated signal was of circular polarization, the received power in each plane was recorded for 2 orthogonal directions, namely for angles of alpha equals 0 and alpha equal 90 between the receiver horn antenna and the sweep path. So this is a relative phase shift, thereby completely capturing the received power. To measure the measured radiation patterns indicate a symmetric pattern, obviously, with respect to the bore site of theta equals 0, which is consistent with our expectation from a symmetric radiator. The total radiation pattern can then be calculated using the vector summation of 2 cases, these 2 measurements, one at alpha equals 0, the other one at alpha equal 90 degrees. If we do the vector summation, we can calculate we can derive the overall measured total radiation pattern of this antenna. As not surprisingly, it's symmetrical, and the measurement is done at a distance of 8 inches between the device under test, in this case radiator, and the received horn antenna. So shown in this slide is the measured phase noise. The spectrum of the down-converted signal is measured by signal analyzer of a Keysight signal analyzer, indicating an RF frequency of 114.1 gigahertz of the radiated signal. The radiator achieved a minimum phase noise of minus 99.3 dBc per hertz at 1 megahertz offset. Please pay attention to the fact that this phase noise is the phase noise of the radiator plus the resonator. This is not the phase noise of only the oscillator. This is the oscillator and radiator together. And this is the best and lowest phase noise ever reported by any millimeter wave integrated radiator so far. This low phase is mainly attributed to the high quality factor of the cavity resonance and the noise reduction due to the coupling of the loop ports to the cavity. So the cavity structure mainly is responsible for the phase noise. By the way, the phase noise could have been much lower if the cavity was used only for oscillation purpose and not for oscillation plus radiation. Because as we know, if we as soon as we insert the slots on the top metal layer in order to radiate the signal, eventually the phase noise is degraded. Yet the minus 99.3 dBc per hertz at 1 megahertz offset phase noise is the best noise reported by a radiator at this frequency. So shown here are the EIRP with respect to frequency and the DC power variation. The HPT bias, the HPT base current and supply voltage are swept in this case to study the impact of the loop impedance variation on the oscillation frequency. EIRP remained within 3 dB of its peak from 113.5 to 114.4 gigahertz. The high quality factor resonance of the cavity leads to highly robust oscillation frequency in the presence of supply and bias variations. The EIRP stays above 6 dBm, and the oscillation frequency only varies by less than 1.3 gigahertz, around 1%. while the DC power varies by 100% through different combination of collector and base biases. So shown here is a table of performance comparison. So this radiator achieves a circularly polarized radiation. It is only a one single element array that also acts like an oscillator, radiator, and power combiner. And it achieves the best EIRP per DC power efficiency, and it achieves the lowest phase noise recorded by literature. Of course, all these phase noise that you can see, they should be scaled properly in order to provide the fair comparison. So in conclusion, an overview of the frequency generation techniques at millimeter wave frequencies was provided. Achieving high output power, low phase noise, and wide tuning range are among the most challenging issues in regard to millimeter wave frequency generation synthesis. A study of oscillator design at millimeter wave was provided. Circuit techniques such as inductive tuning and varactor tuning, incorporating loss and compensation networks were discussed. In designing a millimeter wave PLL-based synthesizer in silicon, the co-design co-optimization of the VCO and next stage divider would lead to far better performance compared to other conventionally used techniques. Also, I introduced millimeter wave circularly polarized signal radiator. In fact, I kind of discussed that millimeter wave circularly polarized signals are highly useful for various emerging applications. Multi-port signal generation radiation scheme offers a number of advantages, including high output power, high DC to RF efficiency, and we can use a single antenna solution in order to produce a circularly polarized radiator. A new cavity-backed antenna structure in silicon was introduced, which offers very high quality factor resonance, multi-port signal generation, and circularly polarized radiation. The amplifier loop and the amplifier loop surrounding the cavity, together with the cavity, were designed for maximum power and efficiency. The cavity-backed multi-port circularly polarized radiator is capable of achieving 14.2 dBm EIRP with 5.2% DC to EIRP conversion efficiency at 114 GHz. So the references are shown here. And toward the end, I would like to acknowledge my former students, PhD students, in particular, Dr. Payam Nazari, Professor Jung Wang, and Dr. Liu Xiang, and Dr. Vipul Jain. And I would like to acknowledge Tower Jazz Semiconductor for chip fabrication global foundries, especially Mr. Ned Cahoon for providing chip fabrication through global foundries. I would like to acknowledge Samsung Advanced Institute of Technology and Global Research Outreach Program for providing support for this research, and also National Science Foundation Awards. And finally, Keysight Technologies, especially Nima Shafiq, right now is with Inphi Semiconductor and Dave Ha for providing test equipment. Thank you very much.
Very well. So I think we have a few questions piled up. So let's go through those. So the first question, I think it might have to do with the earlier slides. The question is, how fast could we change the frequency of these oscillators based on these frequency tuning mechanisms? Could the professor please comment on these frequency tuning mechanisms if we want to do modulation by using frequency tuning mechanisms for FSK transmitters?
Okay, got a good question. So about FSK, so it depends on FSK at very high frequencies. Using inductive tuning is quite possible. Of course, we need to make sure that the current controlling the inductive tuning here, like for example, let's go back here. So the main contributor for inductive tuning in this particular architecture was the tail current here, right? So if the tail current is varying properly by the incoming signal, then we would be able to vary the inductance almost linearly with the current here. And as a result, we can introduce a tuning, and also we can kind of perform FSK modulation. In fact, FSK modulation using this structure is quite feasible. About how fast or the fast acquisition of how fast the tuning range is, again, it is not really that difficult, that different from the varactor-based NC-VCOs. The startup of the oscillation is really dependent on how strong the negative conductance is. If you can have a very strong negative conductance, then the startup would be faster. So it really depends on the strength of the negative conductance that leads to how fast the startup operation or condition of the oscillation would be.
Okay. Next question regarding oscillation radiation. First question is how to ensure the 45-degree phase shift between the stages. Are any phase shifters used?
That's an excellent question. So how to ensure the 45-degree phase shift? So using two approaches. First of all, the 45-degree here is really achieved by the symmetry of the structure. So we want to make sure that this 8-port octagonal cavity is very symmetrical, and the symmetry itself yields 45-degree together with what we have here. If you look at the surrounding amplifier stages, they are also injecting the signal through the CPW feed lines to the cavity. And these two combinations, again, making sure that it is rotationally symmetrical, the layout is rotationally symmetrical, and also this loop surrounding this network, all contributing to this 45-degree phase shift variation. And also we designed the matching circuit such that other modes of operation taking place at other phase shifts will be dying down. And the only mode that is extracted is the one attributed or associated with this 45-degree phase shift. So therefore, to make it to summarize it, the symmetry of the structure and also the surrounding active multi-stage active load, active network that is used here together with the matching circuit to guarantee 45-degree phase shift.
Okay, the next related question is, how do you control the impedance of the module for oscillation? What is the mode of the slot as the second resonance is utilized in radiation?
Right. The mode of the slot in this case, we are using the TEM mode, which is really kind of given by the CPW line in order to make sure that the CPW line feed line can basically create enough negative conductance or inject the negative conductance here, right? Or to this cavity. We basically use the TEM mode of this CPW line. And what was the other question?
The first part of the question was, how do you control the impedance of the module for oscillation?
So how can I control so the control is really governed again by the surrounding structure, right? So the impedance of this, let me go back here. So the impedance of the cavity is pretty much determined by the size of the cavity, by the size of the slots and the length of the slots, and also pretty much by the elevation of two metal layers. So imagine that there is a metal layer here and there is another metal layer underneath. So we are using a cavity, right? So the elevation or the height of the cavity, the size of the cavity, and also the size of the slots pretty much determine the driving point and impedance of this structure. And as you can see, this driving point impedance is dependent on the Z parameters of this multi-port cavity. Now, how can we make sure that the oscillation condition is satisfied? Mainly making sure that the overall impedance here and here is zero is by designing the surrounding network here. Look at this, by designing the matching network and the active devices surrounding the structure such that this condition is satisfied. In the steady state, the overall admittance at each node contributed by the loop plus the driving point admittance seen at each port of this multi-port cavity resonator are summed up to zero. And then the oscillation will be guaranteed.
Okay. Next question. Why is the radiation not symmetric along 0 degrees and 90 degrees when the circuit appears to be symmetric?
That's right. I mean, this is kind of, remember that first of all, our measurement was really done using a linearly polarized antenna, right? That's that. And also the cavity structure itself, we are using an on-chip cavity, right? And the on-chip cavity, the elevation between the topmost metal layer and the lower part constituting this cavity was very small. So therefore, some of these kind of attributed to the structure of the cavity. Some of these is attributed to the way that we basically do the measurement, perform the measurement. We don't have any circularly polarized receiver antenna. We are using a Horn antenna to capture the signal and conduct the measurement.
Okay. Next question. How large is the area and volume of the cavity?
Excellent question. So This is the structure itself is 2.4 by 2.4. This is considered the core cavity structure. The diameter is 1.5 millimeter. So this is 1.5 millimeter. So the cavity itself is around, like, we can assume it's like 1.5 by 1.5.
Okay. Last couple of questions. What tool chain was used to build the cavity radiator? And how do the simulation results compare with the measured results?
What was the first part of the question again?
What tool chain? I'm guessing what kind of softwares and...
Okay, we use HFSS. And what was the second question?
So that HFSS was used to build and simulate and design the cavity resonator. Is that radiator rather?
Use HFSS in order to build the cavity, to completely simulate and build the cavity. Yes.
Okay. The second question is how do the simulation results compare with the measured results?
Good question. So the oscillation frequency, as is predicted by oscillation by simulation, is, look at this, 115 gigahertz, around 115 gigahertz. So what we achieved is 114.1 gigahertz.
Oh, okay. Nice. So very close.
at least oscillation frequency is very close. When it comes to the phase noise profile, perhaps, you know, there is a deviation. Because we are also radiating the signal. Radiation itself cannot be fully captured by the simulation, but at least we were able to, the frequency of oscillation comes very close to what we did. This is let me go back to the back of a slide. I have a back of a slide here that I can. And by the way, in case you guys want to see what is the structure of this cavity, the way that is this layout, the cavity is kind of shown here step by step. As I said, I didn't have time to go through the structure of the cavity, but if you're interested, you can simply refer to our paper. But nevertheless, let's go back to so if you look at the oscillation is for all the ports are the same. This is the simulated out of the HFSS extracted structure, and the oscillation is at 115 gigahertz frequency.
Okay. So I think those were all the questions we had. So I think we have come to the end of our talk. So I want to take this opportunity to thank Dr. Payam Heydari for giving us so much of his time. This was a very good talk, very interesting. And thank you very much, Professor. And thanks also to all of our audience members. We hope that you found it as informative and exciting as we did. So we have more talks scheduled. We have the next talk will be next month, third Wednesday, same as this month. The talk will be in the field of wireless power transfer. The speaker will be Dr. Alex Lidov, formerly CEO of International Rectifier Corporation. So that should be a very interesting talk as well. So we'll be sending out all the details of that talk soon. If you registered for this talk, you're part of our mailing list, so you'll be notified. Also, this talk was also recorded, and we'll be posting the links to the video and the slides in the next few days. So once again, if you registered, you will receive those links via email. So thank you again, everybody. Thanks again, Professor, and we'll hope to see you next time.
Thank you very much. Have a nice day, guys.
Bye.